Yeah, welcome to the next session. Yeah, thanks for that. If you had the opportunity to attend Ingrid's or Srini's talk the last 2 days, you noticed that this might be the most relevant session of CHES, yeah? Since this is on fully homomorphic encryption, and actually its specific topic is acceleration. And looking at the works, I think I found it very impressive that obviously all teams working in this domain and presenting today have actually a cross-continent background, and so it took obviously the wisdom of several continents to finally get all these works done. Yeah, that was quite impressive to me to see that. Our first work is already it's final, yeah, that's what it says, yeah. Now, hopefully not the last one for today, but it's 14 bis, and it's a team from Karl Leuven and University de Campina, Brazil, and is given by Jonas. So, Jonas, the floor is yours.
Thank you.
You want this one? Or you take your own.
Is this one good? Perfect. Yeah. All right. So, this is a talk on both how to build a very fast TFHE accelerator, but especially a talk on how to build a really good NTT. So if you're in the audience and you're like, I'm gonna yeet that ID for PQC, you're gonna have to be faster than me in getting the paper published, just saying. Okay, so I'm gonna explain this using factories. For the people who don't do FPGAs and are just here for the homomorphic encryption and haven't really looked at FPGAs, an FPGA is like a factory. And just like a factory designer, you want the maximum output. That's what you're being paid to do. And you do that by stuffing as many machines on the factory floor as possible, because you have a limited factory floor. So the more machines you stuff in there, the more throughput you get. So something like this is good. This is really good because maximum throughput, right? Every machine working at full capacity, fully pipelined, that's what we call like a conveyor belt system, that's a pipeline. This is what you really want. So, first you have to analyze what are you making. Well, what we're doing from like homomorphic encryption is a whole series of operations, but from a hardware designer perspective, you care about the blind rotate because computationally, that's all there is to it. And if you look at the blind rotate, well, what you're really talking about is number theoretic transforms. Do the number theoretic transform right, and you do the rest of the circuit right. You'll still have to put the rest of the circuit on your FPGA, but honestly, the entity is the most important. Now, an entity consists of butterflies. That is these operations. Something that consists of doing a modular addition, a modular subtraction, and a modular multiplication. Of which, of course, the modular multiplication is the most difficult one. So you need two things for fast TFHE, ideally speaking. You need a circuit that is primarily butterflies. So like your FPGA should, by weight, so to speak, or by area, be basically only butterfly circuits. And those butterfly circuits should be tiny, so you can fit as many of them as possible. Because you can basically consider a TFHE blind rotate a number of butterfly operations that need to be performed. Put enough butterfly units on chip, put enough machines on chip that could do butterfly operations, and you have a fast TFHE. All right. So to do the butterfly, we need to do the modular multiplication. And how can you do this? Well, if you've been around in the conference, you've already heard Montgomery multiplication. Then people looked at Montgomery multiplication and were like, yeah, but for TFHE, the modulus is often constant. Since the modulus is constant, you can do other operations. And these, because you can figure out like this modulus can be customized, like this modulus perhaps has a cool little Hamming weight. Maybe your modulus is something like 2 to the 16 plus 1, and then you know that the 2 to the 16 is actually equal to -1. You can do some fancy stuff with it. But you still have to do some stuff. All these things, like in a factory, are kind of handcrafted stuff. It's like doing it manually. And the problem with doing it manually is that you need a lot of space. You're wasting a lot of factory space with these kind of solutions. Because each of these solutions requires extra operations. While really you want something, what you would really want is for your multiplication to just do the reduction for free. You don't want to do the reduction. You want a modular multiplication to just be as expensive as a multiplication. And with this paper, you could do that. So if you were sleeping until now, now you have to wake up, look away from your screen for one slide, this is the important part. We're going to show you a technique that allows you to do modular multiplication for the price of just the multiplication. All right, how do you do this? Well, first of all, you must realize that if you're doing an NTT, all your twiddle factors are constants. And your modulus is a constant. And both these operations can be written as a function where you take an input, you multiply by your twiddle factor slash e to the power of something, if it's an FFT slash whatever, and you do modulo q. So it's a 20-bit input, if you're working with a modulus of 20-bit, 20-bit output function. And this is a linear function, because multiplying by something is linear, and doing modulo something is linear. So you can split it up into smaller parts. You can split it up into smaller parts, into smaller functions. Into smaller functions that take 5 bits each, for example, if you're doing this with 20-bit. And then you have 20 functions that take 5-bit inputs and 20-bit outputs. Or, well, 4 functions that take 5-bit inputs and 20-bit outputs. And then you sum them afterwards. So the next thing to realize is on an FPGA you have these things called lookup tables. Now lookup tables are just a table that takes a couple bits of input and outputs 1 or 2 bits as output, which is perfect for making these, because if you want to make a function that contains 5-bit inputs and 20-bit outputs, you just need 10 lookup tables that are 5 to 2s. And on, for example, Xilinx platform, LUT 5 to 2s, that's what the whole FPGA is made for. This is also the same way you make a multiplication, by the way. So like some people might be looking at me and being like, wait, that's just how you do a multiplication. Exactly. If you do a multiplication, you're doing the exact same thing. But now you get the modular reduction in it for free, because you consider each multiplication part of the reduction. In fact, you get it cheaper than your multiplication, because when you do your multiplication, you're getting 40-bit outputs. And in my case, we're not getting 40-bit outputs, we're getting 20-bit outputs, because we're doing a modular reduction. So what we end up doing is having 4 functions f, which we need to add together. We just need 20 lookup tables for these functions, 40 lookup tables in total, and 3 instances of a 20-bit conditional adder to get the result. So how does this end up looking? Well, you need your lookup tables, you add the results together, and then you get a 22-bit number that you have to reduce further. Now you might point out, well, okay, but you have to do more in TFHE. Like not all your things that you're multiplying with are constant. Sometimes you have to multiply with, I don't know, your bootstrapping key. That's fair. Then we can use k reduction, which is less efficient, but it still works pretty well. And for most multiplications are still in the number-theoretic transform, because the number-theoretic transform is an n log n operation, and multiplying with the bootstrapping key is an O(n) operation. And the best thing of all is to realize that we don't actually need this final reduction. We just need to do the lookup tables and then adding together. Sure, the end result is 22 bits, because we're adding 20-bit results together, not 20 bits. But we can do lazy reduction. We can reduce that at the very end. So we only have to do the whole thing at the very end. So if W is a constant, we don't need multipliers. We just need lookup tables. Or more to the point, all our LUT-based multipliers just become modular multipliers for free. Now the best modular multiplication circuit you could make for 20-bit TFHE, as far as I know, is the K reduction circuit I just showed you. That requires 136 LUTs and 1 DSP. You need the DSP for the multiplication. The DSP, for the people who don't do FPGA stuff, is like a multiplier circuit. They're available on the FPGA. This thing, that's this, that requires 120 LUTs. On average, because lazy reduction means the size slowly grows, so as you go further, you're going to get a bigger size. Now we have to build an NTT. And now people who are hardware designers might already be saying, well, okay, this is ridiculous. Sure, if you could do constant multiplies, this would be fair, but you can't do constant multiplies because you have butterfly circuits and you have to feed in the twiddle factor, and that twiddle factor changes. So what I say is, well, that's up to the NTT designer. I'm also the NTT designer, so I get to pick how I do this. And I choose to make an NTT that only uses constant twiddle factors. Now one way of doing that is to say I'm going to just implement the whole NTT on it, like the full 1024 by 10. Now, there's a little bit of a problem with that. If you take like one of the biggest FPGAs out there, if you take a U55 or a U280, you might be able to fit like a single one of these entities, like 1024 by 10 or like 512 by 10, but you're not going to leave any space on the FPGA for anything else in the TFHE. And also you need more than one entity anyway, because TFHE needs to do an entity and it needs to do an inverse entity, and reusing that entity is annoying. So instead we do the following. We use the 4-step entity, or you can also see it as like a sort of matrix entity, however you call it. The point is very simple. Take your 1024 coefficient entity and see it as a matrix. First, do entities of size 64 on it. You have to do 16 of those. And then do 64 cases of entity 16 on it. And if you do that, these entity radix 64 elements, these red blocks here, they all have constant twiddle factors. The twiddle factors in those red blocks, they don't change. We still have to do some twiddle generation, because if you do a 4-step entity, one of the steps is doing a linear multiplication with these multipliers. So, I mean, for those, yes, you will have to use the K reduction, but again, that's an ON step. That's not an ON log n step. You'll need ON multipliers there. In fact, you'll need 64 multipliers there. Well, for our butterflies, we'll need 32 times 10. So 320 constant multipliers and only 64 non-constant multipliers. So since the majority is these really cool butterfly circuits, we can fit a lot of these entities on our chips. And we can use an algorithm called final for this. So final is, I guess, kind of TFHE, but better. Like, it does all the things that TFHE does, but it has a smaller bootstrapping key. And it has a bunch of other nice things. So I highly recommend the final paper for more information on this. But the short of it is, you need to do less entities. And you get to use 20-bit moduli, which is nice for me as a hardware designer, because it means my butterflies become smaller. The bootstrapping key also fits on the FPGA, which is really nice because it means I don't have to make a complex interface. I don't have to go through the Vivado tools more than I need to. I just have to feed in this bootstrapping key once from the outside, and then I can keep on reusing it. So there is no question of a roofline model. The only thing I have to worry about is, can I actually feed in my ciphertext into the FPGA, and can I feed it back out again, which is only 1024 coefficients of 20 bits. And also Final has a simple open source license-free implementation in C, which makes it easy to make a hardware design, of course. So this is the final design. Of course, in terms of size, that external product is going to be much larger than the CMUX or any of the other logic. Each entity takes about like 45,000 LUTs for a total use of 600,000 LUTs. Certain parameter sets of previous designs, like FPT, which is also known under the name VBTV, were very well chosen. So if you compare, say, straightforward Final with the absolute best parameter optimized TFHE with all the tricks done, then that best parameter optimized TFHE is going to be better because Final has not been updated for a little bit and the literature moves fast. But in the end, you could kind of claim that compared to the other hardware accelerator that gets similar results to us, FPT, we're slightly faster, just out of the box, but you could argue they make it almost to our performance mainly on the strength of their algorithm rather than the strength of their hardware design. And then these are the current results. It runs at 305 megahertz. It does 31,000 bootstraps per second with a latency of 1 millisecond and an area of, well, between 600 and 850,000 LUTs depending on what you're looking at, and 2,000 DSPs, which is only 20% of the DSPs on chip. Any questions?
Yeah, many thanks, Jonas, for the nice talk. Are there any questions? Yes, please.
Thank you for your last talk. So far as we know, for the entity with some kind of unfriendly quotient. We are using some, for example, CRT to do the entity. We pick up some friendly quotient and then do entity, then use CRT to build it back. And I'm not sure if how do you apply your network to construct the CRT part.
So you mean for CKKS, for example, or like BGV or any of these where you get like a 600-bit 600-bit non-prime, like a 600-bit composite modulus, and you split it up into smaller ones? Okay, so yeah, obviously, to go, if I can go back enough fast enough, probably not. But like obviously this breaks one of the assumptions that I had here, which is that we expect Q to be a constant. And also W will not be a constant because W depends on Q. But you could still make it work, right? Because what you could say is, well, okay, our Q's and our W's might not be constants, but or big modulus prime, we can choose that, right? That's part of the parameter set. We can set that to be, and then we know all the Q's that are going to come out of that, and by definition, then we also know all the W's we come out of that. So then it's a question of being ambitious enough and stacking enough FPGAs on top of each other, because you could make a different entity for every single modulus, right? Now, of course, then you run a bit into the problem that with some of these schemes, not all of them, but like if you're talking BGV or CKKS, that you're discarding the moduli as you go. Like you go with your big prime, and you take your first modulus and you throw away that first modulus, and then you move to the second modulus and you throw away your second modulus. And then you would have empty FPGAs or like empty entity modules that are not doing any computation. So then it becomes a question of stacking enough modules on top of each other, really. In my opinion, you should fully pipeline that thing. If something goes empty, you should just make sure that it gets another task to be done. And that requires some intelligent control logic, but I think that can be done.
Okay.
Of course, that requires you to be willing to batch a lot, but you're already doing that for CKKS, so what's another factor 1,000 parallelism between friends, right? I mean, you could argue indeed, like this will ruin the latency, and it will ruin the latency a little bit. But then again, if you're using CKKS, you've already kind of gone for the max throughput path, not really the latency path.
Okay.
There's some trade-offs to be made there, but you definitely can't use it in the traditional paradigm of CKKS where you feed in your twiddle factors.
Okay.
Thank you. Any further questions? Then I have one for you. In Ingrid's keynote, we saw actually that energy plays an important role, in particular to FHE acceleration as well. Did you do any energy considerations on your work and how much it would cost regarding a kind of operation and the energy consumption for that?
So I did do it because it is generally requested by the reviewers to like do this. It ends up at something, I think I got 90 watts or 100 watts. I'm personally not a fan of the energy calculation of Vivado. I find it a bit of a random number. Like mine ended up turning out better than the other paper, so it was sort of an advantage for me, I guess. But I kind of dislike the number I get. I don't know.
The instantaneous power or energy you're looking
power.
at?
For energy, I don't know.
That would be interesting also to see, right?
If Vivado would give me an energy number, I'm willing to just throw it in there as well, but I don't know.
Yeah, of course. Yeah, that's my question, if you have any estimators used for having an idea what's ongoing there.
I imagine it should be somewhat decent in the sense that I'm using very few DSPs compared to the other groups. I'm using many more lookup tables and much more hardware that just stays constant, like that stays on the chip, that uses the primitives as they go. But I don't know how to properly calculate that.
Okay, yeah, fair enough. Thank you. Okay, then let's thank Jonas again. And I would like to ask the next speaker to stage. So again, we see a very nice collaboration between TU Graz and Samsung Korea. And the talk is called READ, Chiplet-Based Accelerator for Fully Homomorphic Encryption. So from FPGAs, we now go to chiplets. And Aikata is going to give us a talk. Please.
Thank you. So my name is Ekta, and I will be presenting this work, which is a joint work between with Ahmed and Sujoy from TU Graz and Sunmin and Maxim from site Samsung Electronics. I will start with an introduction to the problem statement. We can broadly classify different implementations of homomorphic encryption schemes into 3 types. We have the software implementations, which are quite slow compared to plain text computations. Then second, we have FPGA implementations, which bridge this gap by 2 to 3 orders. And then we have dedicated chip designs, ASIC-based implementations, which hold the promise of bridging this gap by 3 to 4 orders. And in this work, we will be looking into this aspect of custom chip designs. This is clearly not the first work in this direction. There are several prior works that have proposed custom chip designs for homomorphic encryption. And all of these works propose a monolithic chip design, meaning a large chip for accelerating homomorphic encryption. And these chips are often as large as 400 millimeters square. And at this large size, they face the problem of practical realization feasibility. Why? Because of low manufacturing yields. For example, at 100 millimeters square, the yield is 95%. But when you go to 400 millimeters square, the yield decreases to 67% only. And this, in turn, increases the cost per chip. Such large chips also have extremely high fabrication cost and long time to market, almost more than 3 years. And routing and timing closure are also a lot harder on such large chips. So at this point, we ask ourselves the question, what's the way to go forward from here? And if we have to take inspirations from some of the big companies such as AMD, Intel, or NVIDIA, we would know that the answer here is chiplets. So what are chiplets? Chiplets are small dies that can be put together in a package or system to form a much larger complex system. For example, we can have multiple smaller compute chiplets that can be connected to each other and to the memory units via interposer and then put on package for computation. So this is just an example of what a chiplet-based architecture looks like. And it has several advantages. Using a chiplet-based architecture design improves yields and results in high cost efficiency. For example, a monolithic chip, which has a 67% yield, can be increased to 90% if we are able to achieve the same chip using a 4-chiplet design. Similarly, it also reduces the fabrication cost because instead of manufacturing or fabricating a larger chip, we are only fabricating smaller chiplets. It has shorter time to market and simpler routing and timing closure. Another very important advantage of chiplet-based designs is scalability. So if properly designed, you can have a chiplet-based architecture featuring only 2 chiplets up to 8 to 16 chiplets based on different application requirements. And this is a very important advantage of having chiplet-based architecture designs. So with these advantages of chiplet-based architectures, we ask ourselves the question, how can we design a chiplet-based architecture for fully homomorphic encryption? And to answer this question, we take a very high-level overview or a look at what monolithic chips look like for schemes such as CHES, BGV, and BFV. So they generally have 3 compute components, main components, entity, MAC, and automorphism units, which are fed to by large on-chip memories or large off-chip memories such as HBM. And a naive way of realizing this using chiplets would be to form a chiplet for each of these main components. But as you can see here, this is a heterogeneous chiplet-based design, and data and tasks are not evenly distributed across chiplets. So in this case, automorphism chiplet would be sitting idle for most of the time, whereas NTT and MAC would be busy computing and communicating the whole time. And since inter-chiplet communication is slower than intra-chiplet communication, communication will become the main bottleneck in such designs. Therefore, we move to homogeneous chiplet-based design, where the idea is to have smaller monolithic chips, if they can be scaled down, and then connected as multiple copies. In this case, data and task distribution are not a problem. They can be evenly distributed, so we solve the previous problem. but we still have two big problems. The first is inter-chiplet communication is a lot slower than intra-chiplet. And in this case, as we can see, these chiplets will still require a huge amount of communication to be done during operations such as key switch. So in this case, we have a huge communication overhead. And the second problem is we do not know how to scale down the existing monolithic chips in the first place to achieve such an architecture. Specifically because of the way their entity or automorphism units are designed, they're not exactly scalable, and scaling them down is an even difficult work to reduce the area. One way to reduce the communication overhead is to increase the amount of memory on each chiplet, but this will in turn increase the area of chiplet, which will defeat the purpose of going for chiplets in the first place. So we don't want either of these approaches. They're just offering a trade-off. They're not offering a good solution. What we want is the best of both worlds. We want small chiplet, and we want that they can be communicated in a linear ring-like manner. And the good news is, we propose in this work just that. We propose that this is indeed possible. And how we can achieve this is what I will be walking you through. So first, we'll look at how we distribute data across chiplets. So let's say you have a ciphertext component D modulus a large Q, 16 to 1800 bits. Then thanks to CRT and RNS, we can break this down into smaller residue polynomials, modulo Q0, Q1, up to Q15. Next, if you want to distribute these residue polynomials across, let's say, 4 chiplets, then the best way to visualize this is to take 4 different colors and color them alternately with these colors. And now we say that this distribution should be done in an interleaved manner. So all the green residue polynomials will go to chiplet 1, red to chiplet 2, and so on and so forth. And this is done so that when these ciphertext components start losing the computational depth, that is, they stop dropping these residue polynomials, it happens gradually across all chiplets and not at once from one chiplet. So this will ensure in the long term that most of the chiplets remain utilized and deliver high performance. So now that we have looked at how data will be distributed, we will now see how tasks will be distributed. So operations such as addition, multiplication, or automorphism can be done independently on all of the residue polynomials within the chiplets. They will not require inter-chiplet communication, but the key switch that comes after multiplication or automorphism would require communication. For example, if we start key switch with this residue polynomial in chiplet 4, it will first go through an inverse entity, and then will have to be sent to all the other chiplets so that they can perform their respective entity and MAC operations on it. So what this looks like is a broadcast operation, and this operation will not just be done once, but will be required for every residue polynomial across every chiplet. And this broadcast is expensive because, if you remember, we do not want an all-to-all connections across chiplets because it has a quadratic complexity. What we want is a ring-type communication. So now we will see how we can do such a key switch in a ring-based communication flow. So in a ring, chiplet 4 cannot directly broadcast this result to all the chiplets, but instead, it can send it to chiplet 1 in a feed-forward manner, so via chiplet 3, then to chiplet 2, and finally to chiplet 1. And this can be done for all the residue polynomials, as and when they are evaluated. This communication is done while the chiplets are computing their entities and MACs on these components, but still we see that there is significant communication overhead. For example, the results from chiplet 4 reach chiplet 1 quite late, and until then, chiplet 1 is just waiting for this data to arrive. And we also have a solution for this, and the solution is to decouple these communication with more computation. And what we propose is that chiplet 3, 2, and 1 do not need to wait for data coming from chiplet 4. They can already start computing on their residue polynomials. For example, chiplet 3 can only evaluate inverse entity on its residue polynomial and start broadcasting, and so can 2 and 1. And in this way, we are able to completely achieve inter-chiplet communication and computation decoupling. So no chiplet is waiting for data to arrive from previous chiplet. They're already computing on the data that it already has. And the gap between the two arrival is filled by the entity and MAC computations. So we minimize this communication overhead of slower inter-chiplet communication. So with this, we have now seen how we can do a ring-based communication across chiplets. And this, therefore, brings me to an overall architecture design. This is the 4-chiplet read architecture. We have 4 read processing units connected via UCIe in a ring-like manner. And each of these chiplets are fed by the HBM3 high-bandwidth memories. One read PU, or each read PU, features entity or inverse entity unit at its core. This then feeds to 2 sets of automorphism and MAC units. This is because inverse entity is done on one of the ciphertext components, but then it needs to be multiplied with 2 of the key components. So to avoid any stall in the pipeline, we have 2 of these units. Then these are connected to small on-chip SRAM memories that act as data buffers or cache. And there's an instruction controller that controls this instruction flow, which can be reprogrammed in case the flow or the schedule of these instructions changes over time. We also have a PRNG to generate the public key component on the fly. And 4 of these memories, as you can see, are connected to the high bandwidth memory for loading and storing ciphertext and loading keys, except the one on the right connected to the inverse entity. This memory stores the inverse entity result, which needs to be then broadcasted or sent to the other chiplets. So this memory only participates in inter-chiplet communication across the read chiplets. So this is the overall architecture design. So until now, we have seen that we can support a ring-like communication without any communication overhead. We also have designed an architecture to support it. But we still have one problem. This still looks like a big monolithic architecture. We have not proposed ways to scale the big monolithic architectures down. And the core of this contribution lies in how the entity is designed. When we started this work, we saw that almost all prior works commonly employed a 4-step entity. And in a 4-step entity, you split up or you store a polynomial in matrix format. And in most of these works, this matrix is strictly a square matrix. Then you apply unroll entities, let's say, on the columns, and then an expensive transpose operation is done on this matrix, followed by unroll entity again on the new columns. And this entity had several problems when we wanted to use this for chiplet-based design. First of all, the unroll entities were quite expensive. On top of it, the transpose operation, or the support, or way the operations were supported, was also very expensive. Secondly, this was not scalable. Because of the strict requirement of a square matrix, we were not able to have it supported by low bandwidth communication. So with these 2 problems, we decided to go ahead and propose a scalable and transpose-free hybrid entity architecture. And what we do is we still split the data in a matrix format, but it doesn't have to be a square matrix. It can be a rectangular matrix based on the available memory bandwidth. And instead of doing an unroll entity, we process each row with a pipeline entity. The advantage of using pipeline entity is that the data format resulting from pipeline entity is the exact data format required for an unroll entity afterwards. So we do not need a transpose in between. So we are able to support a 3 to 4-step entity without requiring a transpose. And this is, of course, scalable. So this can be scaled based, so the matrix can be a rectangular matrix, and this can be scaled based on the available memory bandwidth. This is also a bidirectional entity, so you can start with unrolled and then go to pipeline for supporting inverse entity unit, inverse entity transform. And this is what the entire entity architecture looks like. I will not bore you with the details, but I will give you the key takeaways. It avoids expensive transpose. It is transpose-free. It is scalable to arbitrary bandwidth availabilities. And it also does not require large unroll entities. So with this, I conclude the design part, and we now move towards the results. So we synthesized the 4-chiplet read system on 7 nanometer TSMC library, and it reports an area of 96.7 millimeters square, where one chiplet occupies 24 millimeters square. And this design was able to achieve or meet timing constraints of 1.5 gigahertz. We also did cycle accurate simulation for various applications, starting from linear regression inference to encrypted DNA training. And the results show that the system can achieve a speed up of 2,800 to 2,900. What this means is encrypted DNA training that was taking around 29 days can be done in 920 seconds using this 4-chiplet read system. If we compare our works to prior monolithic works, we see that the performance is quite at par with the prior works, and so is the area, while improving yield and hence reducing the cost by almost 15% because it's a chiplet-based design. So this brings me to the conclusion. So READ is the first step towards a chiplet-based accelerator for homomorphic encryption. It achieves very high cost efficiency, and careful design choices have made it a flexible design methodology that can be scaled up or down based on the available bandwidth and application requirements. And finally, its results in terms of area and performance are quite comparable or at par with monolithic works, while it reaps the benefit of being a chiplet-based design. Thank you.
Many thanks, Aikata. We are quite out of time, so we have plenty of time for questions. Yeah, Jonas?
Yeah, so first, very good presentation, thank you. And second, well, I obviously had a transpose unit in my first step at DT, so my first question is, how did you remove the transpose unit from your DT? If it's possible to explain that.
Yeah, sure. So you need a transpose in 4-step entity because you want to use unroll entity for when you first process the columns, and then you want to do a transpose, so then you can again have the rows in column format, and you can do the unroll entity again on it. But instead of processing columns, we instead process rows via pipeline entities. So we're not using unrolled entity combination, we are using pipeline entities along with unrolled entities. And this pipeline entities result in data, which we can directly feed to unrolled entities.
Okay. I will have to read the paper, but thank you. Okay. Thank you for developing this technique. I'll be very interested in reading the paper. Thank you.
Thank you for the nice talk and great work. So I have a question regarding how you model the communication between the chiplets, because as you pointed out, that's a big part of the analysis of the performance. So do you use some special like SerDes IPs, or are you looking at maybe optical interconnects? So how do you go about implementing and then analyzing the interconnect part of the chiplet system?
For inter-chiplet communication, we just use the standard UCIe buses and the benchmarks that they provide. So we don't go ahead and optimize what it already does. We just,
so you're just assuming that you will have good designers who will give you IPs meeting the UCIe specs. Yeah. Okay, that makes sense. Thank you.
Any further questions? Then I have a follow-up question on that one. Actually, we are CHES and we love physical attacks. Are you seeing any problems if you have this chiplet design with the interconnect, that there's a larger attack surface on that by physical attacks?
It could be, but it really depends, I think what Srini answered yesterday, that it depends on the attack model. If it is running in a malicious setting and you want to prevent, for example, fault detection, then you, of course, would have to protect a larger part of the design, and the testing would be more expensive because you first test on chiplet and then after connecting them again. But yeah, it is a possibility, but I've not looked into this.
Mm-hmm. Sure, fair enough. Further questions from the audience? As I pointed out, we still have a bit of time. Then I have another one. Again, maybe the same question to you. Have you actually looked at the energy consumption per operation?
We also looked into power, and we did have some estimates for energy. And we do have better energy consumption compared to monolithic works, because instead of relying on large on-chip memory, we rely on HBMs instead. Mm-hmm. And this reduces the power consumption by a lot for our chiplet-based architecture. But yeah.
Okay. Ingrid.
This is the sizes for Jonas. I have a question on the HBM. You have a simulation model, or how did you, and the same with the inter-chip chiplet communication. On your slides, it's just a red line, but in practice, this is something quite complicated.
Yeah, we have a simulation model, and we assume that HBMs can offer this amount of bandwidth, let's say, and then that's why we have some on-chip cache to handle this buffering in between, and we have the same for the interchiplet.
So this ICIe interface technology works, that's communication HBM to HBM?
UCIe is for interchiplet, and then for HBM to chiplet, we have the NOC and these fuzzy layers, which exist for connecting them. But yeah, we just use them as simulation models.
It's just this one. Okay, thank you.
Any further questions? And I maybe continue with one. I was really amazed seeing that you're going for 7 nanometer technology. Is it actually about to be produced in masses and we can buy it very soon?
7 nanometer, I think, could be produced in masses, but I'm not sure if we will have this soon. It really depends on Samsung here.
Yeah, that's right. But there's no plan that actually, we saw some application and hints to that, but there's not just no roadmap for this product. Yeah.
As of now, no. As of now, it only can influence design methodologies for future designs, but yeah, let's see.
Okay. Any further questions? Last options. Nobody? Then I think let's thank Aikato again. Thank you. And I would like to ask the next speaker to stage. So then I do a more lengthy introduction maybe at this point. So we had already an FPGA as an accelerator. Just we saw a chiplet solution. Now we go for the GPU option. I think we're pretty full spectrum in that sense. Yeah? And this work is on GPU acceleration on FHE and TFHE. And we will have here a large team from Taiwan, from Inventec and the NTU, but also from the US, from Washington State and University of Albany. And we have Mingxing giving the talk. So Mingxing, the floor is yours.
Thank you. Hello, everyone. I'm Bess. I work at Inventec Corporation. We collaborate with National Taiwan University, Washington State University, and the University at Albany. This work aims to accelerate FHEW and TFHE bootstrapping using GPU. From earlier presentation, you should have some idea about FHE. It allows us perform computation directly on encrypted data during processing. So neither the data nor the model is ever revealed public during processing. This technology has different applications. It's widely used in cloud computing and preserving machine learning, where protecting sensitive information during computation is critical. There are 3 common FHE schemes. All of them face increasing noise during computation. Noise ensures security, but too high, the decryption will fail. To manage this, bootstrapping refresh ciphertext by reducing noise, but bootstrapping is very slow. We choose FHE and TFHE for 2 reasons. One reason is they use smaller key and the parameter, which fits better within the GPU memory constraint for efficient implementation. Second, they offer faster bootstrapping than other schemes. But their implementation lack the SIMD support. This creates a strong opportunity for GPU acceleration. By leveraging GPU parallelism, we aim to greatly speed up FHEW and TFHE bootstrapping. Now, let's look at how bootstrapping works efficiently on GPU. Bootstrapping requires a lot of polynomial multiplication, which involves data representation transformation, for example, NTT or FFT, and dot product computations. This is highly suited for GPU acceleration. Moreover, GPU has inherent parallelism. This is effectively make up for the lack of SIMD support in FHEW and TFHE bootstrapping. As a result, the bootstrapping process is both faster and more efficient. But we are not the first use the GPU. There are two important prior works. They make FHE schemes much closer to practical usage. From this work, we learned using FFT is faster using NTT. As a result, these works focus on 80-bit security, and their parameters are hard-coded in the library. This makes them low flexibility. Scaling to 128 security bit is difficult. In summary, low flexibility and limited scalability remain key challenges for broader adoption in practical systems. To overcome this challenge, we made 4 key contributions. First, we support security parameter up to 128 bit and even higher, like 256 bit. Second, we consider FFT precision loss to revise bootstrapping error function. We analyze this both theoretically and experimentally. This helps us find efficient parameter within the acceptable error range. Third, our implementation is very fast, achieving over 3,000 times faster than one single-thread CPU, and still 100 times faster than multi-thread CPU. Finally, we apply our method to application and perform end-to-end implementation optimization. This includes secure neural network inference and private decision tree. With this contribution, let's dive deeper into how we achieve this. Start with data distribution and noise analysis. Now we will explain how we achieve such acceleration. First, I introduce bootstrapping algorithm and the key component involved. The process is consist of 4 major components. ACC is a set of polynomial called accumulator. G-decompose is a procedure decompose polynomial to control the noise during bootstrapping. FFT and IFFT perform the data presentation transformation to enable efficient polynomial multiplication. Multiply boot key refers to polynomial multiplication between ciphertext and the bootstrapping key. Next, we will look at how bootstrapping runs efficient on GPU. Previous works typically place the entire bootstrapping into one thread box. But when the parameter grows larger, put the whole bootstrapping in the one thread box, not achieve more efficiency. To address this, without changing the algorithm, we distribute the data across multiple thread boxes. Specifically, we assign one thread box for each decomposed ACC component. Thanks for the new CUDA supports synchronization across multiple thread boxes. Allow us to synchronize thread boxes when necessary during bootstrapping. By distributing data this way, we effectively support large parameters and improve overall performance. Since the bootstrapping computation is distributed across multiple thread boxes, this thread box may be scheduled on different streaming multiprocesses, just like the figure on the right. This assignment of thread box to SMs is handled automatically by GPU hardware and runtime scheduler. Next, we will compare the performance of single block and multi-block approaches. We compare this design under different parameters. As the BG decreases, the number of threads and memory increase. From figure A, when an entire bootstrapping fits into a single thread box, both single block and multi-block processes have their own advantages. However, from figure B shows that when bootstrapping requires more thread blocks and multiple bootstrapping runs concurrently, the performance will decrease. This is likely due to overhead from using more than 2 SMs, causing less efficient memory and higher synchronization costs. Figure C shows memory use exists shared memory size. Here, multi-thread method improve efficiently by better distribution, memory, and computation. Besides modified data distribution on the GPU, we also analyze the noise during bootstrapping. Because we use FFT, the precision loss from FFT accumulates during polynomial multiplication and addition. Ignoring the loss leads to underestimate the noise and wrong error choices. So we revise the error function to include FFT precision loss. These precision loss affect the ACC computation. Since precision loss in polynomial can be modeled as Gaussian distribution, It accumulates during summation. In incorporating this into revised error function, we can select the most efficient parameter that keep error in acceptable range for the application. Besides theoretical analysis, we also conducted extensive experiments to verify the actual noise. From experiments, wait a moment. From experiments, we observed that the decryption value probability under this parameter is below 2 to the minus 32. These decryption value probability are within a controllable and acceptable error range. Next, let's evaluate the bootstrapping performance. We test the bootstrapping on different functions. Compared to fully utilized all CPU thread, a single GPU achieved up to almost 20 times. Scaling to 8 GPU, the acceleration is even more impressive, reaching up to 150 times faster. These results clearly demonstrate the significant and practical improvement boost we achieved. We also measure bootstrapping scalability on different functions. When used a small number of GPUs, the scalability is close to ideal. However, as we use more GPUs, the non-parallelizable parts significantly limit speed up. For example, the figure shows this clearly when using 8 GPUs. Overall, the scalability performance is still acceptable. Around the same time, TFHER's a state-of-the-art GPU acceleration library was updated. We compare our method with TFHER's. On single GPU, our implementation is generally faster, with the best cases nearly twice as fast. Our method is more practical because we optimize end-to-end implementation. It's running any number of bootstrapping simultaneously. Each bootstrapping can use a different lookup table. This capability is especially useful for secure decision tree, where each node corresponds a different lookup table. Beyond spinning up bootstrapping, we apply our method to real-world applications like secure neural network inference and private decision tree. For secure neural network inference, we apply our method on MNIST. We compare our results with previous works. Our method is clearly faster than others. With similar GPU computing power, our method achieves up 1.4 times speed up. For private decision tree inference, we apply an iris dataset. We encrypt the feature of the data and while keeping the model in plain text. We compare our performance with other works. our method is also faster than other works. Especially, we are 5 times faster than pixels. Our method also can apply to larger model and complex data set. This work apply our method to VGG9 model and Cyber10 data set. This results show competitive performance in both speed and memory usage. We are honored that this paper was accepted by PATH 2025. A subsequent work also accelerates FHEW and TFHE bootstrapping using GPUs, but they focus different from us. They primarily optimize NTT computation. Interesting, their methods support NTT and FFT. Combine their acceleration method with our data analogy technology, put potential for the speed up bootstrapping. To sum up, this work tackle the major bottleneck in FHE and TFHE bootstrapping speed by leveraging GPU acceleration and a new parallelism scheme. Our approach pushes performance boundary and apply directly to real-world application. We show significant speed ups and reliable noise control through analysis and experiments. This makes fully homomorphic encryption more practical. Looking forward, we plan to explore new GPU technology like TensorFlow. This effort will further improve computation efficiency. This brings us closer to practical, higher performance encrypted computing that preserving privacy without slowing down. Thank you for your attention. I hope this talk gives you a clear insight into how GPU acceleration can empower homomorphic encryption for complex applications.
Thanks for the wonderful talks. I'm particularly interested in your direction when you break the single block into multiple blocks. So are you going, is this because you want to focus on the latency, reducing the latency? And how about the throughput aspect? Because in some cases, latency is not everything. If you have a lot of data, maybe you can sacrifice the latency, but look at the throughput. That is my first question. The second one is very easy. Is there any plan for you to open source the code like the COFHE? Thanks.
You mean the throughput about when we using the application, your question is mean why we not focus throughput?
Because the single block way, they do it because they want to focus on the throughput. So you can pack everything in one block and you run, it will be easier. But if you break it into multiple blocks, you need the synchronization, the block-wise synchronization. So usually people do that because they want the latency to be lower, and it seems like different design approaches. So my question is that you guys targeting latency, that's why you do it that way?
We also parallel many bootstrapping one time, but I show the result just show latency. But in the real application, we also use the mainly bootstrapping for the one time because, for example, the previous decision tree, they have many nodes in this tree. We conduct this node for the one time. So we also our method also supports parallel one-time use. This is for the first question. The second question about open source. We have planned to open source, but need more data because the work is cooperate with company. This maybe the company agreement. I can also open the open source.
Okay, thank you.
Any further questions, Siming Xing? Please.
Just a very short, silly question. You mentioned that the GPU acceleration with FFT is faster than NTT. So I just want to confirm that when you are saying NTT, you mean the coefficient is on a predetermined finite field, while when you are using FFT, you are considering the coefficient to be a complex number, right? Okay, thank you.
Further questions? Then I have one or two. My first question would be on the FFT. Did you actually make use of the NVIDIA entity, the QFFT, or did you implement it your own?
You means why we just use FFT, not NTT? Because we learned about previous work, the FFT is faster than NTT, and the GPU floating point is more powerful. So we choose the FFT.
But did you use implement your own, or did you just use NVIDIA libraries for implementing
yes,
it?
just use NVIDIA library.
I see. Okay, thanks for that. And with all your work, as you pointed out that you want to look at the tensor cores as well. Do you find anything what you missed while testing and developing for all the different FHE schemes? Would you like to have, for example, more instructions added to the GPUs that support FHE better in the next generations?
You mean why the tensor core can support?
In particular, if you have, for example, any misses, what you would like to see that would still continue boosting your applications and your implementations. Yeah, what is your expectation from the tensor cores to accelerate your implementation?
We mean the tensor core maybe speed up our method because we can do many bootstrapping for the first for one time. Maybe it can transfer just like matrix computation. So this structure is suited for tensor core. So I think tensor core can help our work speed up.
Okay. Any further questions? So maybe I have a little last one. If you'd like to get back to slide 12. Yeah. Can you move back to slide 12?
12. Wait a moment.
All right, a few slides, I know, sorry. Here we go. Yeah, I was a bit surprised about your comparisons. You're saying it's 3,000 times faster with 8 times the GPU versus a single-threaded CPU, and I assume you refer to the RTX 4090, which is a 600 watts device, and if you put it up, you have 5 kilowatts of computing power versus one single-threaded CPU. Is it actually a meaningful comparison, or are you assuming you have a very high potential 5 kilowatts single-threaded CPU in that sense?
Pardon me, you can say again your...
The comparison 8 GPUs versus a single-threaded CPU. Do you think this makes sense from the power budget?
We also compare one GPU, but I just show our more efficiency results. So I just put the 8 GPU from here. But I also compare one GPU, another result.
I see. Okay, then any last chances to ask Mingxing for a question? That seems not the case. Then many thanks, Mingxing, and let's thank Mingxing and all the speakers of the session.